Hi, this is Schwartz, and this is video AB32. The topic is Transcendental Functions and Integration. It covers the AB manual, pages 189 through 191. Hi, this is Schwartz. We know how to use the power rule, some trig rules, and use substitution for integration. We now expand our ability to integrate with transcendental functions using the inverse relationship of derivatives and integrals. Because the derivative with respect to x of the natural log of x is equal to 1 over x, then the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Because integration is tied into an area under the curve, and the ln function is only defined for positive numbers, we then say that the integral of 1 over x dx is the natural log of the absolute value of x, not just x, plus c. If u is a function of x, then we can say that the integral of 1 over u du is equal to the natural log of the absolute value of u plus c, or sometimes stated the integral of du over u is equal to the natural log of the absolute value of u plus c. We now have 6 expressions that, when we integrate, it involves the natural log function. Most of them involve setting up a u substitution. One is the easiest. The integral of 4 over x dx is simply 4 natural log absolute value of x plus c. 2 reads the integral of 4 over 3 minus 6x dx. We'll set this up with a u substitution. U is equal to 3 minus 6x. Du is equal to negative 6 dx. We move the 4 to the outside, multiply by negative 6 on the inside, and divide by negative 6 on the outside. So we end up with 4 over negative 6, integral of negative 6 over 3 minus 6x dx, and that reduces to negative 2/3 the integral of du over u, which is negative 2/3 the natural log of the absolute value of u. Final answer, negative 2/3 natural log absolute value of 3 minus 6x plus c. 3 reads the integral of 7x over x squared plus 4 dx. U equals x squared plus 4, du is equal to 2x dx. We move the 7 to the outside, multiply by 2 on the inside, and divide by 2 on the outside, getting 7/2 the integral of 2x over x squared plus 4 dx. And that becomes 7u, integral of du over u, which is 7/2 natural log absolute value of u. Final answer, 7/2 natural log absolute value of x squared plus 4 plus c. Hi, this is Schwartz. Numbers 4, 5, and 6 involve taking integrals of expressions using trig functions. The technique that often works is writing the integrand as a fraction and letting u be the denominator or some part of the denominator. Then you hope that du is part of the integrand, not encompassed by u. In number 4, we're asked to take the integral of tangent of x dx. We can take the derivative of tangent, but to take the integral of tangent, we will write it as sine x over cosine x. We let u equal cosine x, and therefore du is equal to negative sine x dx. We put a negative to the inside of the integral and a negative to the outside. So this becomes negative the integral of du over u, which is negative natural log absolute value of u, and the final answer is negative natural log of the absolute value of cosine of x plus c. Number 5 reads the integral of cosine of 2x over 2 plus sine of 2x dx. We let u be the entire denominator, 2 plus sine of 2x, and du is 2 cosine of 2x dx. We can pull this off by putting a 2 to the inside and a 1/2 to the outside of the integral, getting 1/2 the integral of 2 cosine of 2x over 2 plus sine of 2x dx. And this is 1/2 the integral of du over u, or 1/2 the natural log of the absolute value of u. The final answer is 1/2 natural log of 2 plus sine of 2x plus c. Note that the absolute value sign is not really needed because the sine of 2x could be at worst -1, and therefore 2 plus sine of 2x will always be a positive number. You can write the absolute value sign or a simple parentheses as was done. Number 6 reads the integral of 1 over cosine squared of x tangent of x dx. We will let u be tangent of x and du is secant squared of x dx. And we realize that 1 over cosine squared of x is secant squared of x, so this problem can be written as the integral of secant squared of x over tangent of x dx, which is the integral of du over u, which is the natural log of the absolute value of u, and the final answer is the natural log of the absolute value of tangent of x plus c. Hi, this is Stu Schwartz. When you take integrals of rational expressions, your first thought is usually u substitution, with u being the expression in the denominator. But that doesn't always work, as shown by some of these examples. Sometimes the u will actually be the numerator. In number 7, we're asked to take the integral of x over the square root of 16 minus x squared dx. So we will let u equal 16 minus x squared, and du is equal to -2x dx. We can pull this off by putting a -2 to the inside and a -1/2 to the outside, getting -1/2 the integral of -2x over the square root of 16 minus x squared dx. And this is -1/2 the integral of u to the -1/2 du, which is -1/2 times u to the 1/2 divided by 1/2, which is multiplying by 2. Final answer, negative the square root of 16 minus x squared plus c. In number 8, we're asked to take the integral of natural log of x raised to the 4th power over x dx. It is clear that letting u be the denominator won't work. If u is x, du is 1 dx, and what do we do with the natural log of x to the 4th power? So we will let u be the expression in the parentheses, natural log of x, and du is 1 over x dx, which we have. So this complicated expression is really the integral of u to the 4th du, which we know is u to the 5th over 5. Final answer, natural log of x raised to the 5th power over 5 plus c. Number 9 reads the integral of x squared minus 2x plus 1 all over x dx. As in number 8, letting x be u clearly doesn't work, so we reach into our bag of tricks and realize that we can split this into 3 fractions. So this becomes the integral of x minus 2 plus 1 over x dx. And integrating each piece, we get x squared over 2 minus 2x plus the natural log of the absolute value of x plus c. Hi, this is Stu Schwartz. Number 10 through 12 are definite integrals, but they can be taken the same way using u substitution, and you decide whether you want to change the limits or not. Obviously, these problems can be checked using the calculator. Number 10 reads the integral from 0 to 4 of 4 over 2x plus 1 dx. We let u equal 2x plus 1 and du is equal to 2 dx. We move the 4 to the outside, and we put a 2 on the inside and divide by 2 on the outside of the integral. So this becomes 4 over 2, the integral from 0 to 4 of 2 over 2x plus 1 dx. We decide to change the limits. If x is equal to 0, u is equal to 1, and if x is equal to 4, u is equal to 9. So this problem becomes 2 integral from 1 to 9 of du over u, which is 2 natural log of u evaluated from 1 to 9. And this becomes 2 natural log of 9 minus 2 natural log of 1, which is 0, or we can write this as 4 natural log of 3 because 9 is 3 squared. Number 11 reads the integral from e to e squared of 1 over x natural log of x dx. We let u equal natural log of x and du is equal to 1 over x dx, which we already have in the problem. So this problem becomes the integral of du over u. We can change the limits. If x is equal to e, then u is equal to 1. And if x is equal to e squared, u is equal to 2. So this becomes the integral from 1 to 2 of du over u, which is the natural log of u evaluated from 1 to 2. We end up with the natural log of 2 minus the natural log of 1, which is the natural log of 2. Number 12 reads the integral from 0 to pi over 2 of sine x over 1 plus cosine x. We let u equal to 1 plus cosine x and du is equal to negative sine x dx. We can put a negative to the inside and a negative to the outside of the integral, and we get 0, negative integral from 0 to pi over 2 of negative sine x over 1 plus cosine of x dx. Changing the limits, if x is equal to 0, u is equal to 2, and if x is equal to pi over 2, u is equal to 1. So this becomes negative the integral from 2 to 1 of du over u, and we can get rid of the negative sign by reversing the limits and write this as the integral from 1 to 2 of du over u. And as in the last problem, we get the natural log of u evaluated from 1 to 2. We get the same answer, natural log of 2. Hi, this is Stu Schwartz. The other transcendental function that we studied was e to the x. And since the derivative of e to the x was e to the x, then the integral of e to the x dx is e to the x plus c. And naturally, the integral of e to the u du is e to the u plus c. Here are a number of integration problems that involve the exponential function. In number 13, we have the integral of 4e to the 5x dx. We take the 4 to the outside, let u equal 5x, and du is equal to 5 dx. So we need a 5 on the inside and a 1/5 on the outside, getting 4/5 the integral of 5e to the 5x dx. This becomes 4/5 the integral of e to the u du, which is 4/5 e to the u, or 4/5 e to the 5x plus c. 14 reads the integral of x e to the x squared dx. U will be x squared and du is equal to 2x dx. We can do this if we put a 2 to the inside and a 1/2 to the outside, and write this as 1/2 the integral of 2x e to the x squared dx, or 1/2 the integral of e to the u, which again is 1/2 e to the u, or 1/2 e to the x squared plus c. 15 reads the integral of e to the 1 over x divided by x squared dx. In this case, we will let u equal 1 over x, and du is negative 1 over x squared dx. We are just missing the negative 1, so we'll put a negative to the inside and a negative to the outside, getting negative integral, negative e to the 1 over x squared dx. And this is negative the integral of e to the u du, which again we know is negative e to the u, or negative e to the 1 over x plus c. I suggest you take the derivative of this expression and see if you come back to the original problem. Hi, this is Stu Schwartz. 16 and 18 are just slightly more difficult. Remember that we usually let u be the expression in the power of e, but that will not always work, and sometimes we will use other rules. For instance, With a fraction, it is usually a good idea to start with u being the denominator and see if you can pull off the du. In 16, we have the integral of cosine x e to the sine x dx. This is very straightforward. U is sine x, du is cosine x dx, so there's no adjustment that should be made. This is simply the integral of e to the u du, which is e to the u, or e to the sine x plus c. 17 reads the integral of e to the 4x over 4 minus e to the 4x dx. This problem, it's a good idea to let u be the denominator, 4 minus e to the 4x, and du is equal to negative 4 e to the 4x dx. We have everything but the negative 4, so we multiply by negative 4 on the inside and negative 1/4 on the outside, getting negative 1/4, the integral of negative 4 e to the 4x over 4 minus e to the 4x dx. And this becomes negative 1/4, the integral of du over u, which is negative 1/4, the natural log of the absolute value of u. And the final answer is negative 1/4, the natural log of the absolute value of 4 minus e to the 4x plus c. 18 reads the integral of e to the x plus e to the negative x over e to the x minus e to the negative x dx. There's only one chance that this can work, letting u be the denominator, e to the x minus e to the negative x. And the numerator turns out to be e to the x plus e to the negative x dx. And we are lucky, we have it. So this can be done. It becomes the integral of du over u, or the natural log of the absolute value of u. Final answer, natural log of the absolute value of e to the x minus e to the negative x plus c. Hi, this is Stu Schwartz. In 19 through 21, we have definite integrals involving exponentials. We will attack the problem by changing the limits. In 19, we have the integral from 0 to 2 of e to the 2x dx. We let u equal 2x and du is equal to 2 dx, and we can write our problem as 1/2 the integral from 0 to 2 of 2e to the 2x dx. We will now change the limits. If x is equal to 0, u is equal to 0. If x is equal to 2, u is equal to 4. So this becomes 1/2 the integral from 0 to 4 of e to the u du, which is 1/2 e to the u evaluated from 0 to 4. And this becomes 1/2 times the quantity e to the 4th minus 1. Be very careful with e and 0. A lot of times with a 0 in a limit, the expression becomes 0, but not with e. E to the 0 we know is 1. 20 reads the integral from 0 to 1 of e to the x plus 1 over e to the x plus x dx. We will let our u equal the denominator e to the x plus x, and du is e to the x plus 1 dx, which we have. So this problem becomes the integral of du over u. We will change the limits. If x is equal to 0, then u is equal to 1. And if x is equal to 1, then u is equal to e plus 1. So when we integrate, we get the natural log of u evaluated from 1 to 1 plus e. And this becomes the natural log of e plus 1 minus the natural log of 1, which we know is 0. Final answer, natural log of e plus 1. 21 reads the integral from 0 to 1 of sine pi x times e to the cosine pi x dx. U is cosine pi x and du is negative pi sine pi x dx. We're missing the negative pi on the inside, and we multiply by negative 1 over pi on the outside, getting negative 1 over pi, integral from 0 to 1 of negative pi sine pi x e to the cosine pi x dx. We will now change the limits. If x equals 0, u equals 1. If x is equal to 1, u equals negative 1. So this becomes negative 1 over pi the integral from 1 to -1 of e to the u du. We can eliminate the negative by changing the limit order. So we get 1 over pi, the integral from -1 to 1 of e to the u du. When we integrate, we get 1 over pi e to the u evaluated from -1 to 1, or 1 over pi times the quantity e minus 1 over e. I suggest you do this problem on your calculator and show that the answer that you get will have the equivalent decimal value of 1 over pi times the quantity e minus 1 over e. Hi, this is Stu Schwartz. Number 22 is a problem that always shows up on an AP exam. Let capital F of x be an antiderivative of x over x cubed plus 1. If capital F of 0 equals 2, then find capital F of 3. At first, the problem seems straightforward. We integrate the expression, getting a constant of integration c. We then use f of 0 equals 2 to find the value of c, and then we can find capital F of 3. But how do we integrate x over x cubed plus 1 dx? Letting u equal x cubed plus 1, du is equal to 3x squared dx, and we cannot pull that off. It doesn't seem we can integrate the expression. And that happens. Many expressions cannot be integrated. But realize we are not really being asked to integrate the expression. We need to evaluate the integral of the expression at x is equal to 3. We use this thought process to solve this problem and others like it. If the integral of f of x dx is capital F of x, then the integral from a to b of f of x dx is capital F of x evaluated from a to b, which is capital F of b minus capital F of a. So capital F of b is equal to capital F of a plus the integral from a to b of f of x dx. Hi, so let's see this rule in solving the problem. Capital F of x is equal to the integral of x over x cubed plus 1 dx. So capital F of 3 minus capital F of 0 equals the integral from 0 to 3 of x over x cubed plus 1 dx. Or f of 3 is equal to f of 0 plus the integral from 0 to 3 of x over x cubed plus 1 dx. Now, we cannot integrate the expression, but the calculator can. It's an area under a curve. So we use the calculator to find fnint of x divided by quantity x cubed plus 1 with respect to x from 0 to 3, and we get 0.879. So f of 3 is equal to 2 plus 0.879 to get an answer of 2.879. Hi, this is Stu Schwartz. Problems 23 through 26 are variations on the same theme. You are given a function capital F described as an antiderivative of another expression which appears to be non-integratable and asked to find values of capital F at a particular point. These all use the graphing calculator and their ability of taking a definite integral. Problem 23 reads, let capital F of x be an antiderivative of the square root of 4x squared plus 5. If capital F of 1 equals 3, find capital F of 5. We use the fact that capital F of 5 minus capital F of 1 equals the integral from 1 to 5 of the square root of 4x squared plus 5 dx. We cannot integrate that expression, but we also use the fact that capital F of 5 equals capital F of 1 plus the integral from 1 to 5 of the square root of 4x squared plus 5 dx. Using the calculator, we get capital F of 5 equals 3 plus 25.866, which is 28.866. 0.866. 24 reads, let capital F of x be an antiderivative of e to the x squared. If capital F of negative 1 equals 2, find capital F of negative 2. We use the fact that capital F of negative 1 minus capital F of negative 2 equals the integral from negative 2 to negative 1 of e to the x squared power dx. And therefore, capital F of negative 2 is equal to capital F of negative 1 minus the integral from negative 2 to negative 1 of e to the x squared dx. Again, we use the calculator's capability of taking a definite integral and get that capital F of negative 2 is equal to 2 minus 14.990, which is equal to negative 12.990. 25 reads, let capital F of x be an antiderivative of 1 over x squared minus 1. If capital F of 2 equals 0.5, find capital F of 8 minus capital F of 4. In this problem, capital F of 2 doesn't really enter into it, as we know that capital F of 8 minus capital F of 4 is the integral from 4 to 8 of 1 over x squared minus 1 dx. Again, we cannot take that integral by hand, but we can find it on the calculator, and we get capital F of 8 minus capital F of 4 is equal to 0.130. Number 26 looks exactly like number 25. However, you are asked now to find capital F of 8 plus capital F of 4 instead of capital F of 8 minus capital F of 4. We have to use the fact that capital F of 4 equals capital F of 2 plus the integral from 2 to 4 of 1 over x squared minus 1 dx. And that gives us that capital F of 4 equals 0.5 plus 0.294, which is 0.794. We also can state that capital F of 8 equals f of 2 plus the integral from 2 to 8 of 1 over x squared minus 1 dx. And that gives us that capital F of 8 is equal to 0.5 plus 0.424 or 0.924. So therefore, f of 8 plus f of 4 is equal to 1.718. Hi, this is Stu Schwartz, and in our next video, we will revisit straight line motion from the point of view of determining the distance traveled based on a particle's changing velocity. That's coming up in video 33.